The thing that we were talking about right at the end of the period was what the free body diagram would look like for this fan cart. And right at the end of the period, I'm confused because I'm like looking at it this way and the screen that way, and then you guys are looking at it from the other angle. So I drew this backwards to you guys because, or did I? What is the direction of the force that the cart feels? The cart's pushing the air that way. So the air is pushing the cart that way. So I got to swing this around here. I did have it drawn correctly the first time. So here's F, smoosh poosh, cart, comma, air. There is a force in this direction, but it's not felt by the cart. It's felt by the air. So I'm going to get rid of that. Then I got to fix this business. Oh boy, this is all kinds of fouled up, isn't it? There we go. So, smoosh push up. Yep, force from the air that way, gravity down. And so then my FU. Oh no, the marker went away. The FU is pointing the same direction as the force from the air, because that's the force that's not balanced. That's the unbalanced force. Okay, so in a sense, those are the same force there. Okay, got a motion detector hooked up over here, and yesterday we created velocity versus time graph. After talking about it a little bit, we were able to create a velocity versus time graph for the fan cart. And so my question to you had been, what can we do to change the steepness of that graph? In other words, what can we do to change the acceleration? So take a moment and check with your neighbor, and then that's what I'm asking you to pause it over there on the Pear Deck. That's the first question. What can we do? What can we do to change the slope of the velocity versus time graph? Hey neighbor, how are you today? I didn't know we were going to have to do something. And once you've had a chance to chat to your neighbor about it, go ahead and type it in there on the old Pear Deck. Let's see where you land. Let's see what our friends are saying over here. How hard I push the cart. I could put the cart. So let's try that real quick. Let's try how hard I push the cart. In other words, this person is saying if I push the cart less hard, what's that going to do to the slope? Run that by your neighbor really quick. So the graph that we have, I gave it a pretty good push. It got almost all the way over to the motion detector. Give it a better push, right? Got almost all the way over to the motion detector. So I give it a softer push. What's the slope of that graph going to look like? What do you think? Check with your neighbor quick. All right, let's check it out. So I've stored that one. I'm going to hit the button here. What do you think? How do those look? Same. Why didn't how hard I pushed it affect the slope of this graph? Run that by your neighbor.
Oh yeah, because
All right. So let's pop over to the deck, and I'll take your answer on that. Why didn't giving it less of a push change the slope of that graph? Okay, didn't change the slope because the push wasn't part of the free body diagram. Keep in mind, for that constant acceleration part of the graph, the free body diagram is smoosh push from the track, gravity from the earth, and then the smoosh push that the cart feels from the air. My force doesn't factor in there because I'm not touching it at that time. Okay, the only force affecting it is that force from the air, and that's not changed. What else do we have here? Push from the hand doesn't affect the free body diagram of the cart during that specified time. So there you go. Okay. All right. So let me go back a slide then. So what do we have? So how hard do we push the cart? All right, we tried that one, and that didn't do it. We could put the track on an incline. We could change the angle of the incline, change how fast the fan is going, speed of the fan, change the incline or decline of the track, tilt the surface heads on. All right. Stronger fan, let the cart go farther. Change the incline, okay? So two common things there. People want to change the incline of this thing, and people want to change the speed of the fan, okay? Let me tell you this. So as far as the incline is concerned, it's intentional that I have this thing at an angle right now where this cart is pretty CDPM. I'll show you because you're going to need to do this for the lab later. Button. Who's got the buttons? So if I give this thing a push and the fan is not on, it's pretty CDPM, right? I have it set at the little bit of padding under that end that I do so that this thing doesn't really speed up or slow down as it goes that way. If it's CDPM, what do I know about the forces on it? They're equal, they balance, okay? So that's why I have this track set up as it is. If I start to tilt this, you think about what that does to our diagram. If I have it on an incline, and it's been a little while, but if I have this on an incline, now when I put those arrows together, now I'm going to have some FU due to that incline. And some FU due to the fan. It's going to kind of complicate things a little bit. So changing the incline, I do agree that would change the slope of that graph. Okay. I guess we should check that out, shouldn't we? Let's do that real quick. I'm nervous as to how much I can put under that end and still have this work. Let's try that. All right. So I put a little something underneath there. I've never tried this one before. All right, you ready? Ooh, scary. What do you think? Did that do it? Is that different? Yeah. Okay. So now we got not only an FU due to the fan, but an FU due to the people not paying attention. Okay. So yeah, changing the incline, that'll change it. But I want to intentionally have this track so that the cart is CDPM. So I know the only FU is due to this fan motor, okay? And so that was the other suggestion, was to use a higher setting on the fan motor. What do you think? Is that a different slope? Yeah. So the fan motor on the higher setting, we get a steeper slope. In other words, the bigger FU, the bigger the acceleration. You can kind of see that here, okay? Just from this graph. So here's the low setting. If I make a bigger FU with a faster fan setting, I do get a higher acceleration value. So I can kind of keep track of that over here. It seems like, oh boy. What do I want to say here? FU and acceleration are proportional, okay? bigger FU, bigger acceleration. All right, anything else you can think of that will change that slope? Especially those of you that work at grocery stores. We change the force, we change the FU by changing the incline. Those are two ways of changing the FU, incline or higher setting of the fan. That definitely affects the acceleration. Is there something that we can do besides just changing the force that will change the acceleration? So some people are typing in some things that will involve, again, changing the FU. We added friction or something like that. Is there anything besides changing force that we can do that will change the acceleration? And again, a couple of shouts for incline. Incline, again, that will change the force. I've got one shout here for changing the weight. Will changing the weight change the FU? Check your neighbor. So if you think about these diagrams, if I make it weigh a little bit less or a little bit more, will that change the FU here? Run that by your neighbor. And I'll throw a yes, no on the pair deck for that. Where's yes, no? There we go. All right. Will changing the gravitational force change the FU? In other words, when you think about this free body diagram, if I change the weight, is there anything else that's going to be affected by that? Is there anything that's not going to be affected by that? All right, we're split evenly here. Half of you for yes, half of you for no. Mitchell, this was your question. If we increase the weight of it, what changes in the free body diagram?
Force and gravity.
Would be if we make it heavier, right? That's a bigger force then, okay? So think about this. So if we make FG bigger, if the pen works, I get a bigger FG. Will anything else change due to that? Then I will have a bigger smoosh poosh as well, okay? I still have the fan on the same setting. If I don't change that, then when I go to add these together, it'll go up higher because there's more smoosh poosh. It'll go over the same because it's the same force from the air. It'll go down more because there's a bigger FG. But if you look at my FU, this FU should be the same as this FU because it's still the same force from the air. So changing the weight doesn't change the FU. Will it change the acceleration? Let's check that out. Anybody got any insights to that? Anybody in charge of like pushing shopping carts at a grocery or nobody? Nobody's a cart boy or a girl? Have you ever pushed a shopping cart before, Peyton? You just do aisles of smiles and just order it online and they just bring it out to you? Fair enough. Okay. I got these hungry hippos at home though. I got to buy like 6 gallons of milk a week and like several dozen eggs. I pile that crap in there. So I'm well aware of what'll happen here. So let's see here. I'm going to clear the latest run. Okay. So this is our baseline. All right. That's our baseline. And then the question is, what happens if I add some more masses to this? Well, we discussed already, it doesn't really change the FU. Will it change the slope? Bruh. What do you think? Did that change the slope? So we made this thing more massive. What did it do to the acceleration? Okay. What if I make it more massive again? Aye. So what effect does changing the mass have on the acceleration? Bigger mass, what are acceleration? Slower or lesser, right? So that's an inverse relationship, okay? The relationship between mass and acceleration is inverse. Bigger mass, smaller acceleration. Nice. It's almost working. All right. Today you're going to need to get acceleration values from these graphs. The way that you do that is you just click and drag over a section of it. And then there's a tool up top. I don't know. This is like even smaller when I'm projecting. There's a button way up top in graphical analysis called linear fit. Okay. And it'll throw or actually you're going to have to go down in the corner probably and do curve fit. But anyways, I throw that on there and it's going to tell me the slope of this graph. Okay, it's telling me right there, the slope of this most recent graph is 0.1167 meters per second. Okay, that's how you'll get your acceleration data today. Okay, the other thing that you're going to need to pay attention to today is your system mass. So I'll show you over here. You pop on over. Brody's got everything set up. Okay, all right. So come on over here, friends. And so the first thing that you're going to need to do is the thing that I did over there, to make this thing equal. Can you turn that to the button? See if you set it on. All right. So there should be some high-tech leveling devices around in various places. So I'm just going to stash some of this underneath the track. And let's see how close we are to CDTM. Let's start here. So let's go ahead and do the space bar for me. Is that CDTM? I don't even have to look at the track. Try that. So, who's that? What do you think? The CDTM? Oh, double click on this one. Oh, I'm talking about Facebook. Ooh, what do you think? Okay, so let's do that again. Baseball. What do you think? Horizontal? Okay, so that's the key thing first. Get some paper towels under here. Get this thing CDPM. CDPM, it is. There we go. That's balanced. Okay. So then I'm going to unbalance it. I'm going to unbalance it by hanging some stuff off the side. I've got 150 grams here, which everybody and their mother knows is how many units of stuff? Unfortunately, Kate doesn't talk out loud. She just thinks things. Thankfully, I called half it, so I know she's 1.5 there. Yeah, there's 1 newton for every 100 grams. Okay? 1 newton for every 100 grams. We've got 1.5. So I'm going to put this on here, and now you're going to have multiple people in your group. I put 1 athletic person in every group, and their job is to catch the cart to keep it from going off the track, okay? So I'm gonna be very grateful for those of you that are paying attention, that you put the hand steam down here. Okay, but Brody's gonna hit the space bar, we're gonna look at each other and breathe, and then I'm gonna let go, okay? It's not a track meet, you don't have to like 1, 2, 3, go, okay? See that thing that looks like a shark tooth? Okay? We're gonna try to improve on that. All right. So go for it again. Okay. So what I did better that time is I started the card a little farther away. It started too close, and you get some kind of weird rock and Gibraltar thing going there. But on this shark's tooth, I'm gonna click and drag over the part that looks like a line. And not all of it, just a little bit of it. And then down here in the bottom left corner in Graph Tools is Curve Fit. And it says linear, yep, I apply that. And it tells me M right over here, the slope of this thing is 2.181, okay? So somebody's gonna have Desmos open, and I'm gonna put in there 2.181 for the acceleration to go along with this data point. Let's collect it again and just see how reliable that is. All right, do you remember what it did? See if Brody can find the slope. Click and drag. Okay. So we have two values for acceleration. Now, that's one of the columns in the Desmos graph that you're going to need to be making. Okay, it's acceleration. The other one is the mass of everything that's accelerating. And everything that's accelerating is not just this card, which the mass is on it, by the way. It's 496 grams or 446 kilograms. The mass of everything that's accelerating includes this thing. This thing's moving too. So everything that's accelerating is 496 grams plus 150. Who knows, right? West High kids is a good math. All right. So then I'm going to do what we just did with the fan card. For my next, after I've done this a couple times, I got a couple acceleration values to go with 646, right? Then I'm going to add one of these bars. This bar is another 500 grams. So now I have in total, I've got about, so this is about 1,000 grams plus 150. I've got 1,150 grams. Okay, that'd be one of my columns. And then Brody's going to hit the space bar. So he's going to get the acceleration on it. Okay, we get less. There's more stuff accelerating, there's lower acceleration. Okay, so ideally, you're going to have 5 different amounts of mass that you're accelerating. Okay, each time I add on one of these bars, it's only 500 grams. There are other cylinders over here that are a kilogram or 500 grams. So you've got those big masses, and that'll be your data table. You'll have the acceleration on the y-axis, and you'll have the mass on the x-axis. I'll put this up here in a second. Okay. And so you need to have 5 different total masses that you're accelerating. Get the 5 different accelerations for that. Now, what can we change from group to group that will make things interesting? So this group's going to have 1.5 newtons. This group right now over here has 0.5 newtons. Make sure your group's got something different. I'll have a little spot up front to write that down. Okay? So that's the idea. You got okay? So grab a couple Chromebooks, get your lab spot, and let's get after it. All right. Catch you that right now. Cheap seats back here. All right. Get your ramp CDPM first thing first.
Josh, you gotta work.
I don't have the.
I got everything linked for you on the canvas. So if you go to the canvas page, there's a link for Desmos.
Brody, do you have the Apple there?
It's an online application. You don't download it, I'm pretty sure.
That's sound. Never mind.
300?
Well,
Brody, what's your group? Alright, potatoes have 1.5 newtons. Hey, Cree, what's your group called? Cucumbers.
Oh yeah.
Cucumbers have 0.5 newtons.
So we're gonna have like a massive card.
So make sure your group has a different hanging mass from those other groups.
They go as 200.
We'll do two.
Broccoli has 200.
Oh my god. Hey, you're
What do you guys want?
just our number.
Actually, let's try anything easy, like 2.5.
What's what called?
2.5.
Today is Friday, 12/21. You be at the end of that. Tomato.
Yeah.
Hey, party day.
Yeah, we
What up?
Lettuce was 2.5.
Lettuce. Friends, keep in mind the hanger itself is 50 grams.
They go 3.
Who? Pickle and carrots. You know what? My roulade recipe has both pickles and carrots together. It wouldn't seem like a carrot thing. It's good. Yeah. Pickles and carrots and beef. Oh my. Otros. So one more.
Sorry. Yeah, 3.5 minutes.
And what are you?
We are.
What are you?
I forgot.
Eggplant, bro.
Eggplant.
Eggplant. Eggplant, bro. What up?
Over here.
This doesn't fit. Get a different hanger there. Come on. You're at the smart kid school.